The first set of problems to which I will apply the dynamics of circular motion are the flat and banked circular roadway problems. Here are three different perspectives of a car driving around in a circular track, circular roadway. Looking straight down on the track, here's the car moving up the page. If you were to take the camera, the camera's looking down here, take the camera and pretend you're standing on the ground back here, looking straight at the car. You might see something like this. This is supposed to be the back of the car. The velocity vector would then be into the page. The center of the circle would be here, and this would be the radius of the circular track. And then if your camera was somewhere in between, not directly overhead, but somewhat overhead, here I've drawn the car further along in its journey around the track here. So the velocity is always tangent to the circular roadway. That's tough to tell from this picture, but at least here you can tell that the velocity is always tangent to the circle. And let's insert our unit vectors. In the previous video, I called them r hat and theta hat initially. That's what you might call them in a calculus class. Your book likes to call them RT and Z hat. So the T hat unit vector is the one that points tangent to the circle, and it's emanating from the object. Here's the T axis. The r hat vector points along the positive r axis. That's always towards the center of the circle. There's the direction of the r axis, and then Z would be coming out of the page. T turned into R. Use the right hand rule. Put your fingers along T, curl towards R. Your thumb would tell you that Z hat comes out of the board. On this drawing, T would go into the board, and I can represent that with an X. That's like the back of an arrow. R points towards the center. This is R. And Z would point straight up. So you can see a different pair or individual unit vector depending on your perspective. Here, I think we can draw all three. T vector is tangent to the circle, R points towards the center, and Z is pointing straight up. Keep in mind that as this car goes around the track, two of these vectors are going to change direction. Z will always point straight up into the air, but T and R will rotate as the car goes around, so that R is always pointing towards the center, and so that T is always tangent. All right, the question that we're usually trying to answer when we look at this problem is, what is the max possible speed V tangential, we'll just call it V, around the track or around the circular roadway? I think you all have some sense that a typical intersection like Carson and Clark near campus, I do miss that place now that we're all stuck in our homes. If you were going to make a circular turn or semicircular turn through that intersection, you can't do it at 80 miles an hour. If you try to go 80 miles an hour around that turn, for the vast majority of cars, you would just skid right out of the circle. So there's some limit there, and we can use the dynamics of circular motion to analyze that. As with all problems in this chapter, these are the equations that you're working with. For all circular motion problems, in other words, the distance from the origin is constant. That means you're moving in a circle. You've got three equations, F equals ma along each of these perpendicular axes. And this quantity a sub r, it's rather simple if you really are moving in a circle. In general, this equation applied in polar coordinates would have a couple terms in it that you'd have to worry about. But for circular motion, you've only got one term. You can calculate it as v squared over r, or if you happen to know the angular velocity, this might be a more convenient way to calculate the radial or centripetal acceleration. Or if you happen to know the period of the circular motion, this would be the most convenient formula to use. We've also got F equals ma along the tangential axis, and I should probably add a tangential is r times alpha. If you happen to know the angular acceleration, you can calculate the tangential acceleration. But this becomes very simple if your speed is constant. If you're talking about uniform circular motion, this would be the case of uniform circular motion, then alpha is 0, a tangential is 0. The right side of this equation is just 0. For all of these problems, whether you're speeding up, slowing down, constant speed, you can set the z acceleration to 0. If you did have a z acceleration, you would be moving out of this circle, out of the page or into the page. Okay. Well, let me draw a free body diagram first along each of these axes so that I can identify the forces. Let's start with the top view. I'll just match it up with the picture here. So for the free body diagram, if we're looking down on the car, as usual, I'll just represent the car with a dot because I know how to draw a dot. What are the forces on this car? Well, I see, well, this is kind of tough. I see gravity going into the page. Gravity points towards the center of the earth, so we'll call this F sub G. That X is supposed to represent the back of an arrow going in. And then I'll put a little dot for a force coming out of the page. And what would that be? Doesn't the ground have to push up on the car to support it? That's what I would call the normal force. And you may choose to just leave these off because let's be real here. This is hard to interpret. That looks like the letter X and an O and an N. So maybe it would have been better to leave these off. The one force that we can draw easily is the force pushing on the car towards the center of the circle. We know that a car moving in a circle at constant speed has an acceleration that points towards the center. And that means there must be a force towards the center. What could possibly push on this car with a force that's directed at the center of the circle? It can't be gravity, because gravity goes straight into the page. It can't be the normal force, because that's straight out. Well, we've already taken care of gravity, so whatever this force is, it has to involve contact. Something touching the car has to be pushing on it. We're not worried about air drag at regular speeds. We're actually just leaving that out of the problem. The only thing touching the car would be the ground. There is a normal component of the ground's force on the car, but there is also a frictional component. So the nature of this force must be friction, F sub R. I'm sorry, that would be rolling friction. We're actually talking about static friction. Not so obvious, is it? Ask yourself, if you're in a vehicle that's making a controlled turn, should the tires be skidding over the road? First of all, you would hear that, and that's no good. You don't want to be skidding. All you're doing is replacing the point of contact between the tire and the road. That's what rolling is. Now, if you're wondering why the static friction points perpendicular to your velocity, that seems a little odd. Let me just sketch the circle here. Friction is towards the center of the circle. The velocity is in this direction. Here's how I think about it. If this is the circular path and your car is right here, if you're driving in a circle, wouldn't the steering wheel be turned to the left, in which case the wheels look something like this? That's exaggerated, but the wheels are not in the forward direction. They're turned. Now, as for the rear wheels, I'm not so sure. I'm just assuming that the front wheels are the drive wheels. But let's look at those front tires. Remember, the tires are attached to the car, which means they share the car's velocity. If the car is currently moving up the page, so are the tires. Now imagine taking a tire, here you're looking down on the tire, and sure, the tires are rotating, but for a moment, imagine that it's not rotating. You've just set this tire on the ground, and you want to scoot it over the ground in that direction. That's going to be tough to do, right? If you wanted to push the tire in that direction, well, no problem, it would just start to roll. But if you have a tire sitting on the ground and it's inflated, and you try to force it in this direction without lifting it, it's not just going to roll easily. It's going to encounter a friction force that opposes the motion, and that's going to be static friction. You might have some sense that static friction force points, I don't know, that way, this way. hopefully you sense that it is possible to get a static friction force towards the center of the circle because of the fact that those wheels are tilted. Now, you don't really have to be intuitive about all that. You don't have to be able to imagine that. You just need to make the assumption that the static friction force does point towards the center. Okay, well, because I can easily visualize using this free body diagram which forces point towards the center, and there's only one, I think I will start by writing the topmost of these three equations. So sum of the forces in the r direction equals mass times centripetal acceleration. Which of these formulas would be most convenient? Well, I'm being asked to find the maximum possible speed, so it's probably best to go with v squared over r. M v squared over r. Now, on the left side, you would plop in all the forces that you can find along this axis. In this problem, there's only one, just the friction force. But in a more complicated problem, you might have 3 or 4 forces along this axis. Any forces that point towards the center would get a plus sign. If they're away from the center, they would get a minus sign. There's only one here, static friction. Okay, well, I could solve this equation for V right now. In fact, why don't I do that? Some stuff might cancel later, so I will wait. But if I happen to know the mass of the car and the radius of the track, I could solve for the speed, provided that I also knew the static friction force. But off the top of my head, or at first glance, we don't really know what the static friction force is. It's really going to depend. The faster you drive, the greater your acceleration, the greater the static friction force would need to be. I mean, this equation tells us what the static friction has to be based on how heavy the car is, or I should say how massive the car is, how fast you're driving, and the tightness of the turn. Like if you make a very sharp turn, you're talking about a smaller radius of curvature, that would require a greater friction force. So I think you see where this is going. The faster we go, the greater the friction that is required. Well, there's only so much friction you can develop between your car tires and the road. If it's just rained and there's some oily water on the surface of the roadway and you haven't replaced your tires in years, you haven't done the Abe Lincoln test where you take the penny and stick it into the treads and make sure the top of his head is covered to make sure you got enough tread, you may have very little friction. And so if you drive fast enough, you will exceed the max possible friction between your tires and the road, and you'll spin out of the circle. So let's leave this for now and move on to, well, we're going to need the normal force, right? Remember, the max static friction force depends on the normal force. So let's draw a free body diagram for which we can actually see the normal force. And I suppose that would be this one. So for the edge-on view, I'm going to draw a free body diagram corresponding to this picture. Here's my dot that represents the vehicle. Now these are unit vectors. Now I'm drawing forces. Okay, so we've already established the friction is what points towards the center. That's static friction. By the way, the static friction that forces your car to turn, to me, it's almost exactly like when you're running in tennis shoes and you want to turn left, let's say. If you're running and you want to turn left, you would plant your right foot and kind of push off of that foot obliquely. And your foot is not sliding on the ground, otherwise you're going to trip and fall. So when your foot plants and doesn't slide, the force that exists between your shoe and the ground, it's got a normal component, but it also has a component parallel to the ground. We call that friction, static friction. Okay, what's the force that pushes up on the vehicle? That would be the normal force. What's pulling it down towards the center of the earth? That would be gravity. And I purposely drew this vector with the same length as this vector because I know, or I expect, that this car is not accelerating along the z-axis. There's no reason to be accelerating this way. It does have an acceleration that way because that direction is towards the center of the circle. Okay, I'm interested in finding the normal force. So how's about I write F equals ma along this axis? That would be the z-axis. And remember, for all of these problems, you set that net force equal to 0 because the acceleration along that axis is 0. And that tells us very simply what the normal force is. This is one of those problems where it's kind of obvious. The ground has to push up on the car with a force equal to the gravity force. Okay, so now we know that the max static friction force is mu times the normal force, which is mu times the weight. Okay, let's put these two together. This is the largest friction you can have. Let's go ahead and evaluate this at its max value and call that speed the max possible speed. Or we could do it this way. And let me flip this, and I'll say mv squared over r is equal to the static friction force. We know that from the radial axis, but that's less than or equal to Fs max, and we just found that Fs max is mu mg. So let's look at the far left side of this equation and the far right side. Good, I'm glad I didn't plug in numbers yet or solve equations, because I can see that the m's cancel. That's a little surprising. It doesn't seem to matter whether you're driving an F-150 or a little sports car, according to this very simple analysis. Now, everybody knows that a sports car could probably negotiate a tighter turn or could drive faster around this curve, and presumably that's because the coefficient of friction between a sports car's tires on the road would be higher, maybe. Also, we haven't taken into account that if you're driving a double-decker passenger bus around a really tight turn, really fast, aren't you going to tip over? And then we have to talk about center of mass, gravitational torque. We haven't even gotten into that. That's chapter 12 and beyond. So right now we're ignoring those aspects of the problem. Let's solve for V. You see this inequality here? All of this shows that V has to be less than or equal to, I move the R to the other side, and I take the square root mu R G. Now I'm going to put a box around that. Not because you should memorize it, but because expressions like this are going to appear a lot in some of these problems. So when you see something like this, that should make you feel good because you're probably on the right track. Okay, evidently the max speed is this expression because the speed has to be less than or equal to that. What happens if you go faster than that? Well, then your acceleration is large enough that you would require a friction force greater than the friction that you can actually develop between your tires on the road. Okay. Why don't we evaluate this for a reasonable radius of curvature and a reasonable coefficient of static friction. So what I'm going to do is pull up Google Maps, see if I can get the dimensions of a left turn through the intersection of Carson and Clark, and we'll plug that in for the radius. This will be a very crude estimate, but here's a little sketch of the intersection at the southeast corner of our campus, the LAC campus. Here's Carson, is it Boulevard or Avenue? Carson Boulevard, I think. Clark Avenue. And suppose you've left the parking lot next to the D building and you're going south on Clark. You make a left turn onto Carson because you want to get some donuts at that place next to the 605. And for a moment, you are executing approximately circular motion. That's an important point that I have not yet made. You don't actually have to move in an entire circle to apply circular motion or to apply the dynamics of circular motion. At any point in time, if you are currently moving in a circle, then during that time, it would be valid to apply these equations. So for a part of your turn, you are approximating a circle. And it looks to me like the radius of that circle is roughly equal to half of the width of the street. Close enough. I'm just trying to get a rough estimate of the radius of this circular turn. So I'm going to go to Google Maps here, where I pulled up an image of our campus. Home sweet home. And down here where there's a scale indicator, 50 feet is this distance here. Well, that's a little bit longer than half the width of the street. So I'm going to say that the half width of the street is something like 30 feet, which would indicate that the radius of curvature I'm talking about is also something like 30 feet. Okay, well, roughly 30 feet. And we know that 3 feet is very roughly equal to 1 meter. I think 1 meter is more like 3.3 feet. But let's just call that 10 meters. Simple enough. let's find out just how fast you can go. Now, the formula we came up with is that the maximum speed was root mu rg. And I'm switching back and forth between lowercase r and uppercase. It just depends on how the table or figure in your exam or homework problem, how that was drawn. Okay, if you look up coefficients of static friction, I believe that the coefficient between rubber, as in the rubber on your tires, and asphalt or concrete is often something like 1.0. I mean, you want that number to be fairly high. That's the whole point of having rubber tires and a ground made of concrete. You want lots of static friction so that you can speed up quickly, brake quickly, turn, etc. Let's plug those numbers in, see what we find. Now remember, if we plug in SI units, our speed will come out in SI. So don't expect the number, 45 miles per hour would be reasonable. 45 meters per second would be over 100 miles an hour. We know we can't make this turn at 100 miles an hour. At least my Toyota Corolla cannot make that turn at 100 miles an hour. 1.0 times 10 times roughly 10, we'll call it 9.8. We don't even need a calculator. This is basically the square root of 10 squared. So roughly 10 meters per second, or I will use this conversion factor. I could just multiply by 2 and some change, but 10 meters per second, or let's just go ahead and do the conversion, times 2.25 miles per hour for every 1 meter per second. So I'm multiplying by 2.25. That's 22.5 miles per hour. Wait a minute, that sounds a little low. Do you really think all these 19-year-olds peeling out of the parking lot in their souped up cars with the green, god-awful green paint and the spoiler on the back that doesn't actually do anything because they have front-wheel drive anyway, so they don't even get the benefit of the spoiler? Whatever. I don't think every car is coming out this fast, so I probably underestimated the radius of curvature. A larger radius of curvature would mean that you could negotiate this turn faster. Me personally, I probably do make this turn at 20 miles per hour or 10 miles per hour. But at least this number, ballpark, is correct. It's order of magnitude correct. It didn't come out to be 100 miles an hour or 200 miles an hour. We know that's bogus. It also didn't come out as 2 miles per hour, which would definitely be too slow. Sounds about right to me. Now, what if you don't want to drive 22.5 miles per hour around a curve? Aren't there many situations where the cars are going way faster than that and they don't fly off the roadway? Case in point, the Indianapolis 500, I think that's what this is. Granted, the radius of curvature of this turn, if you could look from high above the raceway and look down, first, I don't think it's a circle anyway, but even if it were a circle, or if you modeled it as a circle, the radius would be much bigger than the intersection of Carson and Clark. However, take that radius, plug it into the formula, and you would still find that the max possible speed would be something like, 50, 60 miles per hour. Nobody's going to go watch these cars race at 50 or 60 miles an hour. That's like going to watch old people sprint. No offense to, okay, I put my foot in my mouth. Actually, some people do go to see that. There was a Swedish guy I saw who ran, he was like 80 years old, and he ran the 100-meter dash in 11 seconds. I don't think I can run it that fast. So, serves me right for saying that. But these people are here to watch these cars go much faster than that. So what's going on? What prevents them from flying off the roadway, despite the fact that the equation we've been looking at suggests that they should only go 60 or 70 miles per hour? Well, let me go back to the equation real quick we just came up with. I'll have to rewrite that. We found that your speed needs to be less than or equal to this expression. And I'm suggesting even if you put in the radius appropriate to the raceway at the Indianapolis 500, you would still find a speed much lower than the actual speed at which those cars drive. Maybe you're thinking, hey, it's got to be those high-tech tires they have, real broad tires. Maybe it's special rubber. Maybe the coefficient of friction there is like 2, 3. Well, it turns out that's really not it. It's still rubber on asphalt. I mean, how much more static friction can you get? So I will go back to the picture. There's something subtle there in the picture that you may have noticed, or maybe you know where this is heading because you already read the book, because you're a good student. I hope that's all of you. This is not a flat roadway. The formula that we developed just a moment ago was for a flat roadway. This roadway is banked, not by a severe amount, but it is tilted. If it were not for that bank angle, which is sometimes called the super elevation among civil engineers, if I recall correctly, if it weren't for that super elevation / bank angle, there's no way the cars could go that fast. Same thing for freeway interchanges. Aren't there several freeway interchanges around the Los Angeles area where you can drive 60, 70 miles an hour? My favorite is if you're going on the 105 East away from LAX. That's the only way you should be going when it comes to LAX is away. And you merge onto the 110 North with that really cool view of downtown. You're way up in the air. I think you can keep driving pretty fast around that freeway junction. It's kind of like a semicircle or a quarter of a circle. It's got to be a banked roadway. So let's take a look at the dynamics here, or at the Freebody diagram. And these pictures are a little more difficult to interpret, not to mention to draw. So let's do the edge-on view first. And if I recall correctly, this is actually the only picture we need to turn into a Freebody diagram. Okay, so here's the banked roadway, and the center, let's say the center of the circle is right here. So I'll call this, well, if we put the car here, let's say this is the front of the car now. Again, I'm not a Da Vinci here. I'm not even Picasso. I'm not even Basquiat. That's supposed to be the front of a vehicle. Yeah, I hope so. That you can tell. There's an antenna. Does that help? Okay. This car is currently driving straight out of the page, and it's going to make a big circle and then go into the page here, come back around, go out of the page. So the circle of its, the path that it's taking through space, the circular path, it's coming right out of the page here. Semicircle out of the page, semicircle into the page. And let's go from here to the center and call that the radius of the circle. I could try to draw, if this was the circular roadway, to signify that there's a bank angle, you could kind of draw your car tilted like this. Yeah, that's not any better. Look at the picture in your book, okay? I'm not going to draw the unit vectors this time because I don't want to clutter the page. I'd rather draw the forces this time. But which axis starts at the car and points towards the center? This is the R axis. Since they're coming out of the page right now, the vehicle's driving out of the page, that's the direction of the velocity. Remember, the velocity is tangent to the circle. So this would also be the direction of the t-axis, the tangent axis. This is the z-axis. Let's draw the various forces we can find. Of course, gravity pulls down. This is Fg. Incidentally, I forgot to label the bank angle. So the tilt of the roadway with respect to the ground, I'm going to call that beta instead of theta. Rhymes with theta, not theta. And yes, the ground is going to push on the vehicle. And at the very least, there's a component of that force that has to point perpendicular to the ground, to this, I shouldn't say to the ground, but to the roadway. And another word for perpendicular in this context is normal. So this is the normal force. And that's it. I'm imagining that there is no friction yet. No friction yet. We're going to analyze this banked roadway with friction, but the algebra gets messier. Okay. Well, maybe you're thinking, how can you drive without friction? I mean, the flat roadway, you had to have friction. It was the only force available to accelerate your car towards the center of the circle. Well, we don't actually need friction now because I'm going to resolve the normal force into components. in an earlier part of the semester, we might have called this n sub x and n sub y. But what would be a better name now for this axis? This is, excuse me, this is towards the center of the circle. That's the r-axis. So this is actually the radial component of the normal force, and this is the z component. So we really do have a force that points towards the center of the circle. And that may be enough to keep this car accelerating in a circle. There's got to be a force from somewhere that points towards the center. In this case, it comes from the normal force. And if you think about the flat roadway, if this was a flat roadway, wouldn't the normal force point like this and have no component towards the center? So we do have a component towards the center because the normal force is tilted. Why is it tilted? Because the roadway is banked. Okay. Now, because n is tilted, then there has to be a z component as well. Anytime, I mean, if you've got an r component, there must also be a z component. What does that z component do? I hope you see that it balances gravity. So I would think about it this way. The normal force does two things. It has a z component that prevents the car from accelerating downward like free fall, and it balances the weight of the car. And then it has a horizontal or radial component which produces the centripetal acceleration. That's the source, excuse me, of the centripetal acceleration. So in order to see how this all works out, let's write our equations. And before I do that, let me turn this into a free body diagram. So we'll clean things up. Just a dot to represent the car. I will draw the normal force first. And let me make it long so that there's room to work with here. I will break that up into an R component and a Z component. So this is the normal force. Here's N sub Z and N sub R. And I need to figure out what this angle is. That might be the trickiest part of this problem. Now remember, the normal force is normal or perpendicular to the roadway. So let me just draw a very light line, too light, to represent the roadway. And do you remember that this angle is beta? That's the angle that the roadway makes with the flat ground. So you can call that the bank angle or the super elevation. And now let's do just a little bit of trigonometry here. Okay, well, don't all of these angles add up to 180. Like this whole thing is 180 degrees, but we've already used up 90 degrees here. So what's left over? If this is 90, then this plus this has to be also 90, so that you get 90 plus 90 is 180. This angle is 90 degrees minus beta. So I could label that 90 minus beta, but check it out. Look at this right triangle now. What do the angles in a triangle add up to? 180. We've already used up 90 for the right triangle. So these two angles, the non-right angles in a right triangle, they must add up to 90 degrees. So if this is 90 minus beta, this has to be beta. That's one way of thinking about it. Okay, now that we've identified this angle, we can use the hypotenuse to get the various components. It's time to write our equations. Don't forget about gravity. All right. Let's grab a blank sheet of paper. If you ever hear my voice cut out, because my camera includes the mic, sometimes when I lean forward, my mouth is too close to the microphone, and I think the amplifier goes into what the saturation zone, whatever. So I'll try to avoid that. Which equation should we start with? Do we even need all these equations? Well, let's think about this middle one for a second. Which direction is the t-axis in this picture? Tangent is in the same direction as the velocity, which is out of the page. I don't see any forces out of the page here. And I don't see an acceleration either, because nothing was mentioned about this car speeding up or slowing down. So I'll say uniform circular motion. There was no mention of speeding up or slowing down. So if we were to evaluate this equation, we would have 0 on the left side, since there are no tangential forces. We would also have 0 on the right side because we're assuming that there's no tangential acceleration. This car is not speeding up or slowing down. So the equation that we would write is 0 equals 0, which is the most boring equation you could possibly write. It tells you nothing. So there's no point in writing it. I just wasted that ink and that time. Well, it was an important point to make. So sometimes there's no need to write this equation. You're going to write the r-axis equation and the z-axis. I will start with the z-axis. And I'll say the sum of the forces along the z-axis has to equal. Remember, in this class, all of our circular motion problems have an acceleration along the z-axis of 0. There's no reason that this car should be accelerating out of the circle in one way or the other. So now look at the diagram here. And just to make this clear, up, that's the z-axis, towards the right. If your car's over here and it's making this circular turn, to the right is towards the center. So this is the r-axis. Okay. I've got gravity in the negative z direction, and I have a component of the normal force. Now, do you see that this component is adjacent to beta in this right triangle? So I'm going to take n cos beta. That gets the plus sign. Right? This is the component that points up. N cos beta minus the gravity force has to equal 0. And I suppose I can move that over and just call this n cos beta equals mg. I am going to number this equation because I have a feeling that will help me later. I will call this equation 1. Let's go now to the other interesting axis. Remember, we're not going to do the t-axis. What's going on in the r direction? Well, gravity has no component in the r direction. Do you see why? Gravity is orthogonal to the r-axis. No need to take into consideration the r component of gravity because it's 0. So the sum of the forces in the r direction equals mass times centripetal acceleration. And the only force I see is the opposite side of this triangle. It's the r component of the normal force. And I said opposite, which means we can use the sine function. N sine beta equals, now do I need to give that a plus sign or a minus sign? It's directed this way, which is towards the center of the circle, towards the center. So it gets the plus sign. And since just with the previous problem, flat roadway, I'm interested in the max speed you can drive, or actually it's going to turn out the only speed at which you can drive to stay in the circle. That means I want to use the formula for A that has a V in it. I'd like to know what V is. V squared over R. And I will call this equation 2. All right. We've got 2 equations. And you know what? Let's suppose we're given here. Let's say you're given the coefficient of friction. Wait a minute, there is no friction. Okay, don't need that. The radius of circle, of course we know G. And we need to know the bank angle. You know, what's the super elevation of this roadway? Find V. Maybe you're wondering, wait a minute, which V? Couldn't there be a range of speeds at which you can drive? It's not like there's one speed at which you have to go around the interchange between the 605, or excuse me, the 105 and the 110. If there were only one single speed, bad things would be happening all the time, because how do you drive exactly that one speed? Especially with LA drivers. Come on. Okay, we have 2 equations. They both have this unknown normal force. They both have the known bank angle, beta. We don't know M. I didn't actually state M, but I think we're going to find that M divides out anyway, so we don't need it. Let's solve this for V. Now, there's a couple ways you could do this. You could solve this equation for V and then substitute for N. That's fine. But the quickest way to do it, I think, would be this. Let's flip both equations. So put the v over there, flip this one, and then divide equation 2 by equation 1. And you know what? I'll do the flipping part second. First of all, let me just divide the two equations. So I'm going to divide the left side here by the left side here. I'll divide the right side here by the right side here. And if you're not sure why that works, because you like to think about things carefully, you know, why is that valid algebraically? You know, convince yourself. Take some notes off to the side, see if you can convince yourself that that's a valid technique. Okay, well, I would have a n sine beta on the left side over n cos beta on the left side. And for the right side, I'd have mv squared over r divided by mg. Sure enough, the masses cancel. Hey, check it out, the normal force also cancels. We weren't being asked for the normal force anyway. You know, we could go back and solve for that, sure. And here's what I find. V squared has to be, well, I guess I'll go ahead and take the square root. If you're dividing by r and dividing by g, aren't you dividing by rg? So I will move the rg over here. What's the sine over the cosine? Can't we just call that the tangent? Here's what I get. Root rg tan beta. Whoa. This is not a range of values. This is a single value. Now, are Newton's laws misleading us here? Have we done something wrong? Why are we getting a single value? If you plug in the radius of your roadway and the bank angle, only one number comes out. And of course, it's because we're assuming no friction. What if you were driving around that freeway interchange and you hit the gas to go a little faster? Does your car immediately drift up the roadway? Let's hope not. If you speed up a little bit, what's going to happen is friction will kick in to keep your car in check. So friction is the fudge factor there. It's the force that we've neglected here. If you are driving a little too fast, well, let me back up here. This is the one speed at which you can drive without needing any friction. If you were to try to drive faster than this, some friction would kick in and point down the ramp, or not really the ramp, but it would point down the embankment to keep your car in check. If you then slowed down, I mean, if you're stuck in traffic on a freeway interchange, I'm sure that's happened to you. It's not like your car just slides down the embankment. Friction kicks in and points up the embankment, again, to keep your car in check. So there's a range of speeds at which you can drive if friction is part of the picture. You can imagine if there were no friction, what if this was an icy roadway, zero friction between your tires and the road? If you go too slow around that embankment, you're gonna slide into the guardrail or worse. So this is the speed you can go where no friction is needed. That's kind of cool that friction is not even necessary for making this turn. Let's see if we can estimate this quantity for an actual freeway interchange. And before I do that, can we compare that with, I already threw that paper away, but contrast that with the speed for a flat roadway, the max speed. It was mu rg. Different formulas. They look similar though, which is worth noting. They both have a root rg. Difference is this depends on friction. Of course it does. Friction was the force that provides the centripetal acceleration. Here, no mention of friction because it's the normal force which provides the centripetal acceleration, specifically the r component of the normal force. Okay, so I'm going to pause here and Google a typical bank angle and a typical radius of curvature. I didn't actually have to do any digging on the web because there's a file that's already on Canvas. I made something of a lab activity out of this in previous semesters, but this is in the Chapter 8 files, Cloverleaf Interchanges data. I think this was from a government website, but it's got some actual civil engineering information about real freeway interchanges. Let me show you a picture here of the, yeah. so-called cloverleaf interchanges. I don't think we have a lot of those here in SoCal because there isn't space for them. But here are some typical values. They give the radius of one of those circular clover leaves as you're going from northbound on one freeway to westbound on another freeway. And then they give the super elevation. Remember, that's a synonym for the bank angle, but they don't give it in degrees or even radians. They're giving it in feet over feet. So what they're actually talking about is rise over run. I'll explain this in more detail later, but that is the tangent of the angle. So what I'm going to do is take the arc tangent of one of these numbers. Let's see, off to the side here, I'll say, actually, I don't even check that out. This must be why they do it. Tan beta is what's in the formula. Very cool. So tan beta, let's go with the 0.04. And so according to their information here, the speed should be 25. Of course, that's miles per hour. Okay, let me go back to my notes here. Let's check what the formula says. Let's see if the number that comes out of here is at all consistent with what this civil engineering website gave. Okay. Oh, I forgot to write down the radius of curvature, didn't I? Let's go back here. The 25 miles per hour, the radius was 150 feet. Okay, well, those are not SI units, so we're going to have to convert those first. I'll do that on the back here. 150 feet times, well, 1 meter is roughly 3.3 feet. So we're talking about a radius of 45.4 meters. Okay. And yeah, well, at the end, we'll convert our speed back into miles per hour. All right, we've got the square root of 40, what did I say, 45.4 meters times 9.8 times the tangent of beta. Well, the tangent was given to us. That's the rise over run. It was given to us as 0.04. So that's a very modest bank angle. Wouldn't that be scary if you were on a freeway interchange that was banked at 50 degrees? Or maybe that would be awesome. Okay, 45.4 times 9.8 times 0.04. Don't forget to take the square root. All right. The one speed at which you can drive around this banked roadway, hang on a second, with, that can't be right, 4? What? Let's try this again. 45.4 times 9.8 times the tangent of beta, which is 0.04. Take the square root. Okay. 4 meters per second? Nah. That's like 10 miles an hour. I'm going to pause and see if I made a mistake here. Well, I was not able to find an error in my calculations, and I'm remembering now that the numbers provided by that website come from an analysis that includes friction. Here I've looked for the speed at which you can drive where no friction is necessary. So if you drive at, well, this is roughly, if I take 4 meters per second and multiply by 2.25, that's roughly 9 miles per hour. Okay. If you go at 9 miles an hour around this cloverleaf interchange, no friction is even required between your tires and the road. That does not mean that you can't go any faster, but if you do go faster, friction will have to kick in and be part of the equation. That means part of your Freebody diagram. So the next thing to do would be to return to the Freebody diagram and add another force, friction. Repeat the analysis, get new equations, and get a new formula for the speed at which you can drive. So that is coming up next. So the first thing we have to sort out before drawing the modified Freebody diagram is which direction does the friction point? And what type of friction is it? Well, if you're in this vehicle executing your circle at just the right speed, so that you don't slide down the embankment or up the embankment, what would tend to happen if you hit the gas and went faster? And that may be pretty challenging for some of you to imagine if you haven't spent a lot of time watching these races or you've never driven on an embankment yourself. But I don't know, think about throwing a marble into a bowl. If you throw it faster, doesn't it kind of move farther up the bowl as it's orbiting the center of the bowl? This vehicle would tend to drift up the embankment. So in order to keep it from actually drifting, because we know that if you are traveling around a banked roadway and you do speed up, generally your car doesn't immediately drift up the embankment. You just keep going in a circle of the same radius, but now you're going a little faster. So there must be a force that kicks in and prevents this tendency of your car to drift upwards. That force would have to point down the roadway, and that's the friction. Is it kinetic friction? Is it rolling friction? Is it static friction? Well, rolling friction is associated with driving in a straight line and you want to just coast. I think that would warrant more detailed discussion, but let's just accept that it's not rolling friction. It's certainly not kinetic friction because your tires are still not supposed to be skidding over the roadway. Just like before, it is static friction that prevents you from drifting up or down the ramp. Now you might be wondering, how do we know that it actually points this way? Why not, diagonally, somewhere between the surface of the roadway and the normal force? Well, here's why. If this was the direction of the friction force, and I'm going to go ahead and spoil this drawing now. If this was friction, couldn't you break it into a component like this and a component like this? What would you call this component? Well, that would be absorbed into what we call the normal force. So by definition, friction is a force between the tires and the road, which is perpendicular to the normal force. It's got to lie in a plane perpendicular to the normal force. So now you might be wondering, well, how do we know that it actually points down the roadway in the plane of this page? What if it's kind of coming out of the page too, or like this? Again, we know that's not the case, because if there were a component of force that was parallel to the roadway but pointing out of the page, wouldn't that be making the car speed up or slow down? And the idea is the car has already reached the speed that it's going to drive at. So it's no longer accelerating along the tangential axis. So that thought process leads us to conclude that it has to point down the embankment, and that force has to lie in the plane of the page. Admittedly, some of this is a little difficult to visualize. So that's what I've done here. I've just modified the Freebody diagram. I've added a friction force that points down the ramp. Okay, now about the angles here. We already went through why this is beta, but do you see that if this is beta, since we've got vertical angles here, this must also be beta. And now we are ready to write our this is the Freebody diagram. We're ready to write our equations. Which equations would those be? The same ones that you use for every problem in this chapter. Skip this one. Car's not speeding up or slowing down. We do need to write these ones. Or these two, I should say. These ones, is that even proper grammar? I honestly don't know. But hey, this is a physics class, so you can't judge me. Some of the forces in the z direction have to equal 0, as in all these problems. What do we have? I see gravity in the negative z direction, and I see two components also in the z direction. This one is positive because it's pointing up. This is the side adjacent to beta. This is the side opposite beta in my friction triangle. So I'm going to write n cos beta minus fs sine of beta. I think I did that right. Take the hypotenuse times the sine of beta, that would give me this, minus mg equals 0. Okay? But let's make this assumption right now. let's say that we're finding V max. Let's find the max possible speed that you can drive on this roadway before your car really does skid up the embankment. There's a limit to how much friction you can get. If you keep driving faster and faster, this vector would have to get longer and longer. Eventually, you've maxed out that vector. If you go any faster, you'll skid up the embankment. So Vmax corresponds to Vmax corresponds to Fs max. So we've already maxed out friction, and that means we have an additional relation that we can invoke. It would be proportional to the normal force. That's mu sub s times n. So instead of writing Fs, let's write mu times n. And I will go ahead and put the mg on the other side. I've got an n cos beta minus, well, now I will insert the max friction force, mu n. And some of you are probably thinking, wait a minute, can't you just plug in mg? The normal force, it's just the weight, it's just mg. That is not always the case. In fact, it's definitely not the case for this problem, because if we solve this equation for the normal force, we are not going to get mg. So the only way to know for sure what the normal force is to write an equation that contains the normal force. I think I can factor out n here. Cos beta minus mu sine beta. What am I supposed to do with this? It's not clear yet. I'm interested in the speed. I don't see the speed anywhere in this equation. So I have to continue. What's the one other equation we can write? Well, I've already applied Newton's second law along the z-axis. Let us now apply it along the centripetal or radial axis. Remember, to the right. That's the positive direction. What do we have here? I've got an r component of n, and I have an r component of s, excuse me, the friction force. I didn't label those because I think it would be a little confusing, but this is the r component of the normal force, and this is the r component of friction. So check it out. If you think about it, what is the friction doing? We already established that the normal force does two things. It helps support the weight of the car, but it also provides some of the centripetal acceleration. Friction evidently also does two things. It pushes down, which I would say helps prevent the car from accelerating up the embankment, but the friction also contributes to the centripetal acceleration. Interesting. That's not at all obvious, that dual role of friction. I mean, really the only way to find these things out for sure is to do what we're doing. Apply F equals ma, solve the equations. As far as we know, Newton's second law is the correct dynamical tool for calculating these things. Okay, the sum of the forces in the r direction has to be equal to 0. Is that true? No, it's equal to mass times acceleration. And remember, we're interested in the speed. So let's use the formula for acceleration that involves speed, v squared over r. And specifically, we're talking about, oops, I should have left room here for the force. Okay, I've got, this component is opposite beta, so that will be n sine beta. That gets a plus sign because it points towards the center. This component of friction also points towards the center, so it gets a plus sign. Now, in this right triangle, the r component of friction is adjacent to beta, so I'll say plus Fs cos beta. That's got to equal m v squared over r. And now we'll say use v goes to v max means Fs goes to Fs max, which is mu times the normal force. Static friction is not always simply mu times the normal force, but it is in this instance because we're evaluating this scenario at the max possible speed, which implies max possible friction. Okay, that means we've got an n sine beta plus mu times n cos beta. It's getting a little cluttered here. Just like before, we can factor out n. Okay, sine beta plus mu cos beta equals v squared over r. Oops, I'm switching back and forth between little r and big R. That's a mistake on my part. They mean the same thing. We're interested in, oops, I keep saying oops. I really should have specified, this is the max possible speed, right? V max squared over R. This is what we're interested in. We need to solve for V max. I can't solve this one equation for V max because it contains the unknown normal force. This equation also contains the normal force, however. So how's about we call this equation 1. Oops. Here's equation 2. I'll use the same technique that I used for the flat roadway. No, not for the flat roadway. That was for the banked roadway without friction. So this is really the third problem we've looked at. First, we started with a flat roadway, then a banked roadway, no friction. Now we're analyzing the banked roadway with friction. Just like before, let's take equation 2 and divide it by equation 1. All right. If I take this left side, right, this is equation 2, take this left side and divide it by that left side. I've got n times sine beta plus mu cos. See how messy this is getting? This is one of the longer problems we've done as far as the algebra is concerned. Okay, and on the right side, I have v squared over r. I left out the m here, didn't I? M times acceleration. So I've got an mv squared v max squared over r divided by, it was just mg. Just like before, some stuff cancels. The normal force is eliminated. Fine, we didn't want that anyway. Interesting that it doesn't matter how massive your car is. So whether you're driving a Toyota Corolla or a Toyota Corolla with dead bodies in the trunk, it's going to be the same. And we're solving for V max. We can clean this up though. Now, for a long time, I didn't clean this up. I left it as is. And then I've discovered, I think from your book's solutions manual, there's a nice way to write this whole thing. In fact, I think I'm going to write this right here. I don't have room. Okay, V max squared. I won't do the square root yet. This is 1 over RG, so I'll put the RG upstairs. You've got sine beta plus mu cos beta. Well, do you remember that the PDF I showed you about the cloverleaf interchanges, they liked to express the angle beta in terms of its tangent. So check this out. Let's multiply by 1 over cos beta on top and bottom. Of course, if I do that, I'm multiplying by the number 1, which means I'm not actually changing anything. I'm just presenting it in a different form. Well, when I distribute that 1 over cos beta, you see that it will cancel this cos beta, and it will turn my sine into sine over cosine, which we can write as the tangent. So that cleans this up a little bit. And I'm going to anticipate taking the square root. So I'd have an RG, and then on top, sine over cosine, that's tangent. I'm going to write this as mu sub s, I'll switch the order, plus tan beta over, well, down here I'd have a 1 minus, 1 minus mu tan beta. All right, don't forget your square root symbol. How cool is that? There's one big gnarly formula for the maximum speed at which you can drive. It's going to depend on how big the circular roadway is. Of course, the bigger the roadway, the faster you can drive. That makes sense. Now, it's not a proportionality. There's a square root sign here. So if you give your circular interchange 4 times the radius, the square root of 4 is 2, then you could drive twice as fast. Of course, it also depends on how much friction you've got between your tires and the road, and it will also depend on the super elevation in the form of the tangent of beta. So what I'll do is revisit the cloverleaf interchange data. And I believe I have a spreadsheet on Canvas where I used this formula to try to recover some of the results from that PDF. So I will pause and return. And here is what I did. This spreadsheet could really use some better formatting. I need some bold font here, maybe a different font. But I took the data from the website. I've got a set of different radii for cloverleaf interchanges of increasing radius. I took those distances in feet and converted them into meters. I went ahead and entered the super elevation. Now remember, these are not angles in degrees or radians. These are the actual tangents of the angles. And my formula, if you recall, involves tangent anyway. And I was kind of dumb when I prepared this spreadsheet. I converted the super elevation back into beta because the formula that I originally implemented was the one with the sines and the cosines. I could have done this in a more streamlined fashion. Okay, the interesting part comes in this column right here. You can see this gnarly equation. This is the equation that I just wrote down. Let me go back to my notes here. That equation that you saw in the formula bar of Microsoft Excel was this equation with the square root, of course. You know, I could have entered it like this. That would have been better. So what I did was calculate the max possible speed that a vehicle could safely drive at as they're negotiating the turn of this cloverleaf interchange, because I wanted to see if those values matched up with those in the PDF. So I will return to the PDF. And you'll notice that I get a bunch of numbers in meters per second. It's a simple matter to convert those into miles per hour. And remarkably, they're pretty close. You might be thinking, wow, what a coincidence that it came out to be exactly 15. Well, I'm going to explain why in a second, why these really do match exactly. 20.5, that's very close to the website's given value of 20 miles per hour. It starts to diverge a little bit here. So it's getting worse and worse. But if you look carefully, you will see that in front of the formula that we just derived, I've got this extra number, 0.6117. And if you look carefully, I seem to have chosen a value of 0.8 for the coefficient of static friction. That's my mu sub s. Maybe I should have gone with 1.0 instead of 0.8. But really, it's going to depend on each individual car, right? Doesn't the coefficient of friction depend on the interaction between the rubber of the tires and the roadway? Let me make sure that I'm actually recording here. Yes, I am. Okay, so it's debatable whether you should use 0.8, 0.9, etc. So let me explain what's up with that 0.6117. If I get rid of that, if I just use the formula that we derived, and notice in each case I'm referring to the particular radius in that row and the particular super elevation. Okay, that didn't even come out right at all. Hang on a second. Let me undo what I just did. I don't know what happened there. Okay, right here. Let me get rid of this 0.6117. And I will repeat this new calculation all the way down. Okay, these numbers really don't agree well at all. According to my calculations, if I look across this first row, for a cloverleaf interchange with a radius of 50 feet, and no bank angle at all, no super elevation, you could safely drive at 24 miles per hour. The website only says 15. I find that for a larger cloverleaf of 90 feet and a bank angle with a tangent of 0.02, you should be able to drive at 33 or 34 miles per hour. The website says only 20. So it dawned on me, why would any civil engineer calculate the max possible speed at which you can drive before sliding right off the embankment and then post that on a sign for the public to obey? Because most people don't obey signs. They drive faster than the sign suggests. And you want some fudge room in there anyway as a safety buffer. So what I did was calculate the max possible speed and then say, how about we just go with like 60% of that and post that on the sign. So if I add a little 0.6, let's just take 60% of the max allowable speed and do that in each case. Then we get numbers that much more closely approximate the numbers given by the website. So what I did was tweak that 0.6 ever so slightly until the output here matches the website's value exactly. And I don't even really need to do that because 14.7 is already close to 15. So the last thing to observe would be, there's obviously a difference here. Does this mean that the physics we're using is just cartoon physics? It's unrealistic. The actual modeling used by the civil engineers was a lot more sophisticated? I doubt it. I bet that they used the exact same formula, maybe with a couple of extra terms. You know, you'd have to take into account whether a car would tip over, or would you? For such small bank angles, that's probably no concern whatsoever. Even for a double-decker bus, a super elevation of 0.04 is insignificant, I would think. So the last thing I realized was, again, why would you post a number like 33.53 miles per hour on a sign? They don't even bother to give the units usually. They just give a number. It would make more sense to just round down to the nearest multiple of 5 or round up. I think all of these numbers are reasonable. You know, maybe the last one seems a little off. But if my calculations show that 60% of the max possible speed is 46.8, yeah, just call that 40 miles an hour. Good enough. So I'm satisfied with the agreement between what the physics is telling us and the numbers chosen by this safety commission or civil engineers, wherever this is coming from. Okay, the last thing I'd like to look at is the minimum possible speed. We've calculated the max speed, but is there such a thing as the minimum speed? If you were to drive too slow, would bad things happen? Let's go back to the notes here and make a clever observation. Let's see, stop share. Okay, if I return to the Freebody Diagram, that sounds like the beginning of a Leonard Skinner song. Well, if you're going around and around in this circle and suddenly you slow down, you hit the brakes, certainly if the roadway was slippery, if it was icy, you know your car would start to slide down. So when it's not icy, what's the origin? What's the nature of the force that prevents your car from sliding down? Well, if you're trying to slide down and you don't, wouldn't the friction have to point up the ramp? So we could repeat this whole process by changing the friction force from pointing down I shouldn't say ramp, I should say the embankment, from pointing down the embankment to pointing up the embankment. And that would be a little tedious just because we'd have to rewrite the equations. But check it, there's a very simple way to account for that. How do you take this vector and flip it around by 180 degrees or rotate it by 180 degrees? Wouldn't you just multiply by -1? Well, static friction, Fs max, is mu times the normal force. So multiplying the vector force by -1 could be accomplished by just changing the sign, SIGN sign, of the coefficient of friction. All I have to do is go back to my original result. Right here, this is the expression for the max possible speed. All I have to do is change the sign of mu sub s, and that is equivalent to redoing the free body diagram and rewriting the equations with Fs pointing in the opposite direction. That's pretty cool. And you know, little tricks like that show up fairly often. So I would actually have negative mu s plus tangent beta. I will write that as tan beta minus mu s down here. This mu s would turn into a negative mu s. Negative negative would give us 1 plus mu tan beta. Pretty sneaky, huh? Now, there's one other thing I'd like to say about this formula. I may have a spreadsheet addressing this, so hang on a sec. Okay, I thought I had a second spreadsheet implementing this formula. I do not. It wouldn't be difficult to just modify the formula in the existing spreadsheet, and that should be on Canvas if you'd like to take a look. But what I wanted to point out is if you take a reasonable value for the coefficient of friction, like 0.8 for rubber on concrete, or even 1.0, and you plug in the super elevations that were given in the Cloverleaf interchange PDF, and you include the radii that were given, you get nonsensical results out of this. In fact, Excel will say like error, something to that effect. If you were to do it manually, you'd find that you were taking the square root of a negative number. So I would suggest that the minimum speed is imaginary. What? You can drive as slow as 30 miles per hour times I. What does that even mean? Do you realize what's happening here? The math is telling us that there is no minimum speed, or whatever the minimum speed is. It would be, you're taking the square root of a negative number. That's the square root of a number less than 0. It says what we already know. If it's a dry day, you can stop your vehicle on the 105 to 110 North interchange, and your car is not going to slide down the embankment. It's just going to stay put. There is no minimum speed. That's what the math is telling us. Now, I have been in a situation where the roadway was icy and my car did start to slide. That was kind of scary. If it was icy, this number would be considerably smaller. Yeah, why would this radicand come out negative? Why would we be taking the square root of a negative number? Well, if the tangent of beta is 0.04, if that's your super elevation, and you're subtracting 0.8, yeah, you've got a negative number in the numerator here. However, if you reduce the friction drastically, 0.04 minus something even less than that could give you a positive number. And the math would be telling you there really is a minimum speed at which you have to drive. If you're going around that icy freeway interchange, you might have to maintain a minimum speed so that you don't slide down. Okay, so these problems are a little challenging. That was a lot to go through all at once. You had to draw your free body diagram correctly. You had to analyze it using trigonometry correctly. You had to convert that into equations using this little table of results that you're going to use for practically every circular motion problem. And then you had to do some algebra. All right, next video will be a look at related problems, more circular motion problems. But this last problem we looked at was among the most challenging. So if you followed this, you're in good shape for the rest of the chapter.